right? So I'm just combining elements in my sum to get that. Okay, so does everybody agree with me that if I can give you an algorithm that does 1 and 2, I will be done? Good, I see nods of approval, or at least nobody's willing to admit that they don't. Okay, so how do we do that? Well, again, it's not very hard. In fact, it's almost ridiculously easy. So everything I've shown you right now was in my original proof, but here's the crucial place where the algorithms are different, very crucial. They're both simple, but theirs has a nice, so that's the algorithm. So first of all, you start, as you probably would imagine, with a root labeled, what a root must be labeled, 1. Okay. Now you're going to grow the tree in the following manner. So you're going to partition uniformly at random the descendants of 1. So that is the set from 2 up to n into 2 subsets. I'll call the one subset S, and you should think of S as the left descendants of 1. And also a set T, which of course is going to be the rest of them. So that'll be the right descendants. Okay, so now I've told you one is here, it's S, these guys are going to be on the left, these guys are going to be on the right. And then I essentially iterate, right? Since it's an increasing labeling, what must the left child of 1 be? Well, it must be the smallest thing in the set, right? Because things have got to get bigger. So make min S the left child of 1. And iterate, right? That is to say, break S up into 2 pieces, which are the left and right, and similarly with T. So, quick example. Suppose we start off with, say, 6 vertices that we're playing with. So we'll start off with 1 at the top, and I'm going to record the probabilities here. So I have 5 vertices left. Say we put the vertices 2, 3, and 5 on this side, and we're going to put the vertices 4 and 6 on this side. What's the probability of that step? Well, I'm essentially picking out a subset of the numbers 2 through 6, of those 5 numbers. How many subsets of 2 through 6 are there? 2 to the 5th. So the probability of picking out that particular subset is 1 over 2 to the 5th, right? 1 over the total number of subsets of a 5-element set that I could have picked to go on the left. Of course, we don't need to worry about this, because once we pick this guy is automatic. It's just the rest. So now we do it again. So we've got to have 2 here, we've got to have 4 there, and now we've got to partition 3 and 5, you know, so we might put 5 here and 3 here, say. And then we've got to put 6 and its complement, the empty set somewhere, say put the empty set here and 6 there. So what's the probability of doing that? Well, now that 2 was fixed once we had this partition, and then we had 2 things left over, so the probability of splitting them that way is 1 over 2 squared. And after we put the 4 here, we only had 1 thing left over, so the probability of putting it on the right rather than on the left is 1 over 2 to the first. And now we're done, right? Because everything else, we're just going to have partitions into empty sets. Which don't really do much. So all those partitions are 1 over 2 to the 0. We don't have any choice because we put partitioning nothing. But now again, think what the hook lengths were for this tree. Right? Top vertex has hook length 6, this has hook length 3, this has hook length 2, and these guys all have hook length 1. And you'll see that this is clearly the product over all these vertices of 1 over 2 to the h of b minus 1, right? 6 minus 1 gives you the 5, 3 minus 1 gives you the 2, 2 minus 1 gives you the 1, etc., etc., etc. And it has to be, because think about it. What is this 6 telling you? It's telling you that that vertex has 6 descendants, including itself. So if we're partitioning the set of all descendants not including itself, we're partitioning one less, a set of size 1 less, and that's why you got the 2 to the 5th, 1 less than this hook length. And similar for the rest of these. So I hope it's clear now that 1 there is trivial. I mean, it's directly from the definition of the algorithm. There's nothing more to do. We've built it into the algorithm. We've hardwired it. There's nothing more to do. So 1 is clear. And 2 is easy. So 1 is trivial and 2 is easy, which is the way I like my proofs to be. So why is true easy? Well, let's take a look at this.
Why is it not clear? Because probability.
I'm sorry, what?
The probability distribution. So you have to have the 1.
Well, we don't know that. We haven't proved that that's
Why?
the case, right? That has to be proved. We're just saying, put things down with this probability, but I mean, it's possible we got something which wasn't a probability distribution. So
Yeah, I know.
there is something. Just because we define something, it doesn't mean it's correctly defined. It just means we chose to define it that way.
But the probabilistic process is clear a priori that has to have commands.
In my mind, I mean, we could have defined all of these probabilities to be 1/3, and then of course it wouldn't, you know, they wouldn't sum up to 1. And we could define these probabilities any way we like.
But you decide, you like flip a coin, decide on the left side, and then.
I mean, yeah, I think what you're essentially thinking would go through.
Or you could have phrased it differently.
Yes.
And then you would be.
And then it would be, because of the way I phrased it, we do a little bit more work. But yeah, if you think of it as just for each one thinking